Hello. Let's do a quick review of this hash table code, and we'll fix a couple of things in it before we move on to something else. So we had a bunch of students, and we had one student who had a particular social insurance number who kept giving us a different name every time they talked to us. And so he appears in this table 3 times with 3 different names but the same social insurance number. So we wanted to get rid of the duplicates in that list of things. And the way we did that was we put all of the students into a HashMap, which is the Java version of the hash table, went through and put them all in, and we used the student as both the key and the value. In order for the student to work as the key, you have to make sure that the student class has got an equals and a hash code method in it, because from our code, if you remember what it did, it queried the key to get the unique number, and then it used equals to decide whether or not, when we had a chain of things, it had found the appropriate matching one. So the only way that it's going to work is if you have hash code and equals written for the objects. In this case, hash code and equals just make use of the social insurance number because it's already a unique number, which is the definition of what a key is. So we took those students and we plopped them into the table, and when you put them in the table, we know that hash table is going to replace any of the values that are duplicates, because a hash table operates basically just like an array. You dump something into a particular array position. If you put something else in that same position later, then it just gets replaced. Okay? So that ends up wiping out the duplicates, and then we went through and printed out all of the unique things. And the other interesting thing about hash tables is that there's no iterator, because there are actually 3 different ways of iterating through it. And so you can iterate through all of the keys, which are like the definitions in a dictionary. You can iterate through all the values, which are, sorry, the definitions rather than the words, or you can iterate through the pairs. So we chose to go through all of the values, and so there's there's a function that in the hash table that gives different iterators for different purposes. So this is the one that says go through all the values and print it out, and we saw that we only got the ones that were unique that way. Just out of interest sake, suppose that I wanted to keep the order that these students came in because somehow the order was important. Okay? The problem that we've got is that with a hash table, it specifically disrupts the order because it scatters people about the table, and so you never get the same order out that you put them in. Okay, so you can see here that it's JoJo and then the last couple of Bobs, which is definitely not the order that they came in. So suppose that I want to maintain the order somehow of these things from oldest person to most recent to talk to me, which is basically how they're defined in this table. Okay? How do I go about doing that? It seems like it's going to be an issue. It turns out that it's actually really, really easy. There's a special kind of hash map called, now get this, a linked hash map. And a linked hash map's job is to operate like a hash table, but it will also keep things in order. That's all there is to it. Okay? And if you run this, what we'll see is that these guys will change order now and operate in the order that they actually came in. Other than that, for some reason, it decided it didn't want to get rid of one of my duplicates. But oh no, that's right. I just only showed you 3 of the 4 that were there. So there they are in the order that they appeared, I think. I got that right. Yeah, JoJo and then Bob. Something like that, maybe in reverse order. So not particularly interesting, except that you can use this thing to keep the order if you need to go through it. Okay? So that means you get the benefit of both fast access for storing things and searching for them and replacing them, plus if you ever need to go and look at them in order, they'll come out in order. Okay? And notice also that that's the reason for not using the specific term on that side. I use the interface word on this side. Map and LinkedHashMap and HashMap are both different kinds of map. Okay? And so that means that the only thing I have to change is that one word to get a slightly different behavior for how these things work. Okay? So there's LinkedHashMap. What else happened here? Then we went through and we said, well, okay, suppose that for the duplicates I wanted to see how often they were seen instead of just throwing them away. So we wanted to count the number of duplicates that were seen for each person, which is basically how many times does this person talk to me. Okay? The way we did that was we made a different hash map, and this time we put students into the table as the key, but as the value, we're going to record the integer for the number of times that we've seen them. So we're pairing up a student with a value. So there's that idea of a hash table used to pair up two things that didn't previously belong together, but somehow we think they should temporarily. And we had to use big I integer there because little I integer can't be placed into a table or into a collection because it's not an object. Okay. Went through and dumped all of the students into the, tried to dump them all into the table, so there's the for each, go through all of the list of things, and then we had to worry about whether or not it was the first time we'd seen them or some time after that we'd seen them. So if it was the first time that we'd seen them, we put them into the table with a value, a starting value of 1. It's the first time. And then thereafter, once they'd already been seen, what we did is we retrieved how many times they'd been seen and then bumped up that number and put them back into the table, which replaces the old version. Okay. And I said that little line of code is actually pretty common. You see it in a lot of places. Do the first one specially, then, oh, okay, if it's not the first one, it must be the other ones. We did the same idea in linked list code, actually way back when. The other thing that's weird about this is the fact that we've got this little trick here of having to use big I integer here and having to go out and add values and all sorts of little weirdities. Part of the problem that we ran into is that get by its nature retrieves the thing directly. The other trick that you can play is rather than retrieving it, we could change this to say if times seen dot, try one of the other options, times seen. Notice that hash table has a bunch of unexplored things, and there's one here called containsKey. And so if you just want to check and see something's in the table without retrieving it, which means that you don't get a null back, you can play this game instead. containsKey who, do it that way. Okay, instead, so if it's not in the table, be explicit there. Then what we'll do is we'll retrieve it and clean it up a little bit that way. Okay. Oh, I guess I don't need to do that there. Wrong place. This actually goes down here, which makes more sense. Okay. So now there's probably an easier check. Well, if they're not in the table, then I'm going to add them in specifically with a 1. Okay? So that sense is maybe even better because that little null check went away. Okay? And I think we can actually get rid of that big I integer there, but not worth the trouble. Okay? By the way, while we're on containsKey, there's also times scene dot containsValue, which says go find me the value, see if a value is in the table. Okay? So in this case, it's a little hokey because it's see if something's been, if the number 10 appears in the table. But for other things, it would be if we were putting students in the table, it's go see if, Joe is in the table. Which do you think is faster, containsKey or containsValue? Because
it's just going through the array rather than having to check and see and divide if the array is empty too.
longer explanation, containsKey is efficient because it goes straight there using hash code, versus if you're looking for a value, what do you have to do? You have to go through every single entry in the table to find the value because the key isn't going to operate as a lookup, right? So you'd have to go through, it's basically a linear search, run through each element of the table, run through each chain that you can find, searching for the value. Okay, so they're a little subtle in their usage in terms of which one. So normally, if you're sticking to performance, you would use containsKey. Okay, so that's it for that example. Let's try a different hash table example. I'll just bring up a piece of code here, piece of starter code. Let's try this one. Okay, what I've got here is a table of names and default values for a program. All right, so this is like if you think of a Linux program where you've got command line arguments coming in. Okay, you've got something that looks like this. You run this program, and there's the names and the values that I want for that particular run of the program. Okay, but there's probably a set of defaults associated with the program so that if you run it with no arguments, you just get the defaults. And so what I've done is I've made a table of just sort of arbitrary default names and values. Okay, so the problem here is when I run the program and I give it this as arguments, what I want it to do is replace any of the values that are in here, any of the default values, with the newly changed things. So in this case, I've said I don't want the default of size 100. I want don't want the default of size 10. I want size 100. I don't want the default of height of 20. I'd prefer 25, and I'm going to give myself a name rather than just being anonymous when I run this program. Okay, so now the question becomes, how do I merge all of these things so that I get a table that contains things that are everything along with all of the changed values? Seems like a tough problem. Put them in a hash table. Okay. The joy of putting them in a hash table is that if we put these things in first, a string versus the value that's associated with it, then later on, if I can go and put size as the key and 100 as the value, then that size will replace the size that's already in the table, and I'll end up changing that value. So the trick is really put all of these into the table first to get you the defaults in the hash table, and then parse this line to split it up to put all of those things in second, and those will replace any of the ones that are there with the defaults. Okay, so let's give it a try. Let's make a hash table, which is a map. What's the map going to have associated with it? What are the pairs of things?
String
String for the key and string for the value. So we won't bother. Some of these are strings and some of these are numbers, so we'll just treat them all as strings, and people can figure out the number part later. So this is the completed table for one of something else, or we'll call it the, I guess it's the name table. And we'll make that a new HashMap. And we'll use the quick version now to say there's my new HashMap. Now you want to run through each one of the defaults. What's the for each going to look like? Just love two-dimensional arrays. How are you going to dig those out of the array?
Do a nested for the type of slotty.
Well, remember, these are grouped together, right? So this is an array of 2 strings at a time. So the 0 position in the array, string sub 0 here, contains 2 things. So the row is just one of those things. All right, that will go through all of the things because I've just basically gotten rid of one of the array subscripts. So we'll go through all of the rows in the table and do what with them? You can call both the strings out if you want. So string name is row sub, get this right, we'll do them in the other order, I guess, row sub 1, and the other one is, whoops, and the other one is string value is row sub 0. I think that's right. I don't know. Well, we'll find out, won't we? When in doubt, just do a quick check. We'll print them out the other order. Name plus value. Okay. So if you're confused, let's just try printing them out. And I get 20 height, 10 size, so it looks like it's backwards. So when in doubt, change that to a 1, that to a 0. Height 20, size 10, weight, there we go. Okay, so you can see, again, I'm not much for figuring it out, just let the program tell you and then go, oh, thank you very much. I guess that's the way it should be. Now that we've got them separated out, now what? Put them in the hash table to get the defaults in, so that that's nametable.put, and we want to associate the name with the value. Okay? And there's, by the way, there's Pfeiffer's rule about do the simple thing first, right? So if you put them into variables, you get to think about what those things are, and then you can do something sane with the result rather than putting the table with row sub 0, row sub 1, which would just be sort of weird and not tell people anything. Plus it gave us the option to print it out to see whether or not we got the right things. Okay? So don't do things in a complicated way, and it just makes it easier to write the code. So now we've got the defaults in. Now what? Go through all of the arguments. So we're going to have to parse that stuff. Ouch. How do we parse that line? There's a split it with what? There's a class that will help us on this. Most useful, handy class that you've forgotten how to use from last term. Good old scanner. So the scanner class will parse lines for you. So we'll say scanner, this is line is, actually line's probably a bad word, args, not much better, new scanner, and we're going to use arguments as the string. So the scanner class is lovely for doing a whole bunch of things, including parsing strings, reading from input, right? Okay. So interesting thing about the scanner once you've made it is how do you use it?
Take it out and press it up.
You could do that, but oh, look. Does that look familiar? Meaning scanner has an iterator that will allow you to go through all of the stuff that's on the line. Yeah, okay, well, let's just use the iterator then. So iterators have a while args dot has next to go through all of the things. Now we need to talk to it and get one of the things, args dot, what's going to give us something back. We did has next, keep going, keep going, keep going. Look, next returns a string. Okay. Oops. Well, it's actually going to be a pair of values, so we'll put the word pair in there. Args.next. Just for fun, let's just print out the pair of things and see what we get. Isn't that nice? So
it just looks for white space?
It just looks for white space to split things out, and so we've now split out all of the stuff by white space and gotten the three things now as separate things. Right? Well, that's making progress. So now we can get the pair of items. What do you want to do with the pair of items? Split on the equals sign. So I want to split the pair, right? So let's do it this way. This is probably a little too terse. Let's make another scanner. For single item. And let's give it the pair because, gee, that's also a string. Right? So so now I'm not going to bother with a while loop, actually. I'm just going to try and get the two pieces.
Can you just use strings split?
You could, but scanner will do that. And the joy of scanner is that you can end up using it for other things once you get the technique down. So it works for scanning files, web pages, like across a network. It does all sorts of goofy stuff. So yeah, it does sort of look like all of the stuff that you can do with string, but it's just going to be consistent and be a little bit more handy. So now the problem is that the thing that we have to split on is the equals sign. Change the delimiter so you can do single item dot, it's actually use delimiter, and say, oh, I don't want you to split with that, I'd prefer you to split with equals signs. And then let's just see what we're getting when we split it. So we'll do single item dot next, which is a string, and we'll put that into, oops, string variable, which should be the name. And the next thing that comes, we'll assume these are well formed, so the next thing should be the value. Next thing, and we'll just print those out. And see what we get. Oops, should have put a space in there, but doesn't really matter. There we go. So now I've split them out again. So in this case, instead of printing them out, we're going to turn around and add them into the table instead. And those should replace the ones that are already there. So now we'll go through and print out the table. Thing that we want to get stuff from is name table. What do you want to print out from the name table? The keys and the values together. So we need the pair of items. The thing that prints out the pair of items is that thing. So that will give us the pair of things, and what you get back is entry string string. I did that right. Doesn't know about entry. String string, call it a pair. So the name that comes out of that is a pair dot get key. And the other thing that we can get out of that pair is the value is a pair dot get value. And then we'll print those out. And so in our final product here, we should have replaced size 10 with size 100 at the very least. We'll just run this thing and see whether or not that's happened. So there's size 10 became size 100. Okay, so it replaced all of the values. Okay, so there's a standard little hash table trick, really good for replacing duplicates. And a reminder that the scanner class is really useful for playing with strings and parsing lines of stuff. It's a fairly recent addition to Java, but it does a good job of a whole bunch of things. There's one question about this thing I was going to ask, which I've now forgotten. Oh yeah, I remember what it is. Suppose that somebody mistypes something. What's going to happen? You're going to get a new entry into the table because that's a different word. Oops, probably not what you want. So what do you have to do to correct that?
Check with the name table whether the key already exists.
Got to make sure that the key already exists before you issue the replacement. So this is the part where we're doing the replacement. So before we put it into the table here, there should be an if statement that checks to see whether or not that thing is actually in the table. Okay? So if name table dot, might as well use containsKey, for some reason is false, containsKey name, then at that point we can do something like, for want of something better, because when we're in a main program, we'll print out invalid name and we'll just continue without putting it into the table. And give that a run through. And there you go. Okay, so now you've got a easily working argument processor that you can steal for other programs. Questions about that one? Fast and efficient use for hash tables. Okay, let's move on and let's move on and talk about trees now. Hash tables replace duplicates. What happens to trees with duplicates? What did our code do? It kind of ignores them because they'll make a mess of the tree, because if it's neither less than or greater than, there's basically no place to put it. So things that are the same, we just turned around and threw away and said we're not interested in them. Okay? It turns out that that's a really, really, really useful property, right? To throw away duplicates. And to show you that it's a useful property, I'm going to take you back to your grade 5 math that was repeated, I think, last term in math class, or one of the terms in math classes. Let me just draw something that will bring immediate concern. Does that thing look familiar? Good old Venn diagrams, right? From, what's that? Like I said, didn't they do that in grade 5?
Oh.
Don't they start out with grade 5 with Venn diagrams, and then was it last term then that you did it again?
Yeah, first quarter.
Yeah, first quarter. Okay, good old Venn diagrams. Okay, so what's interesting thing about that area in the Venn diagram?
Duplicates?
It's the duplicates. It's the stuff that's common between here and here. So if you take two trees of things or two sets of things and you do the union of them, you're throwing away all of the stuff that's duplicated between the two, and you've only got one version in there of the stuff that was duplicates. So sets, by definition, you can't have a duplicate in a set. Okay, so Venn diagrams come back to haunt you. Well, why would you ever want to do that? That would be a real life example of where you'd want to actually use that.
Well, there's two lists of, let's say, customers or something, where
Two lists
you
of,
don't wanna,
two lists of customers,
yeah, where you don't want duplicate customers, you know what I mean?
because,
That'd be bad.
but why? Like, I'm trying to think of a practical application.
You don't want
You wanna mail them the same bill twice or something?
You don't want to spam them, or you're gonna email them something and you don't want the email to appear twice. Think Facebook and friends. So this is your friends and my friends are gonna get together and have a party. We've got some friends who are different, and we've got some friends who are the same, and I guess if we're mailing out invitations to everybody to come to this party, we don't wanna mail out that set twice, so we just want with a group of, okay? Or, show me the group of friends that we have in common. Okay, which is what the intersection of those things is, so if you just treat that, you get the intersection. The converse of intersection, right? Show me all of the friends that we have that are different from each other, right? Because you just wanna get to know those people or whatever. So all of the set games you can play with that sort of stuff. How about calendar entries? We wanna find a meeting time for people. So you're saying, show me all the places on your calendar that are not in use, and then we'll take all of the places that you have that aren't in use and all of the places that I have and aren't in use, and we'll see if we can find a place where we agree to come up with meeting times, okay? So any of those sorts of problems, it turns out that that tree feature gives you one of those things, and you can do unions and intersections on trees to get the results that you need. Okay, so let's look at a simple example first. What I've got is a friend class, so I'm playing the Facebook game, and this friend class has got first name, last name, nickname, email, so normal sort of stuff that you would have for the friend. And there's an equals method for some strange reason, and then there's a compare to, and compare to says that friends are ordered by last name, first name, and then email for some reason to try to tell them apart. Okay. So I've got that, what looks like a sort of a standard class that we've done for a long time for ordering things. And so what I've done is I've made up a list of my friends and your friends. And so there's just an array of all of the people that I know, and there's an array of all of the people that you know. And now I want to see the list of people that we have in common. Or let's start out with the easy one. We want to have a party with all of our friends, and we want to send out the invitations, but we don't want to send out invitations twice. So how do I go about getting a list of everybody without any duplicates? Put them in a tree. Well, let's give that a try. So a tree in Java, the official one, interestingly enough, has an interface for set. So you get a set of friends. So let's do a set of my set of friends just to make it look a little different. And we're going to use, I just have to get this right, think about which one I'm going to use. TreeSet. Would I be so lucky? Make sure you get the import statements right. So there's a tree set that's going to have friends in it. How do I get all my friends into the tree? For each would be the sort of the first way that you would think of doing it. So this is for friend, a friend, in my friends, to my set of friends dot add them. Okay, so dump all of my people into a tree. How about a shortcut for that? That gets a little annoying. It turns out that you can make a set. So we'll do your friends the easier way. So there's your set of friends as a new tree set. Every Java collection has the ability usually to take another thing in as a starter. So copy all of these things into the tree. Okay? So what I'd like to say here is just copy all of the of your friends into the tree. Oops, doesn't quite work. It will. This will work for a list, but unfortunately arrays are a little not quite as smart as lists, and so you can't do that because arrays aren't considered a collection. The little trick here is that we can say, let's treat your friends as if it were a list, at least temporarily, and the little shortcut for that is arrays.asList of your friends. Okay, so the logic here is I'd like to use that array and dump it all into the tree. Arrays, unfortunately, can't be dumped into a tree directly, but I'll make them look like a list long enough so that they can be dumped into the tree. And that's just a little convenience method that basically does the work of somehow making it look like a list. Don't have to worry about it. Okay, so now you can do the shortcut for that one if you want to, but I wanted to show you both versions, right? Okay, so now how do we find out the bunch of them? Combine the two trees. Let's do it into another set of friends. The combined set is, we'll make a new tree set. And now, since we have a tree already, we can make a new tree set with my friend set to begin with. I did that right. Didn't spell it right. My set friend. Okay, sure. Yoda talk. Okay, so there's, I'll dump my friends into the combined set, and now I want to dump all of your friends into the combined set. And this is another case where you could write a for each, but since it happens all the time, there's a shortcut for it, which is combine dot add all. Don't be scared by the weirdities in there. We'll just say add all, and this is your set of friends. Okay, and then we can go through for friend who in combined wonder if I made a two-string, we'll find out. Nope. We'll just do their first names. Oops, guess I didn't even do that. I'll get last name, sure. Guess I was a little lazy when I was writing the friend class. And we'll run it through, and there's the list of all of the people that we need to invite. Okay. Notice anything about the order of that? It's alphabetical because the tree is using compare to do the ordering, so you get them in alphabetical order by default because that's the way it does things, which is a reminder that in order to put things into a tree, you better have a compare to, otherwise it won't work. Okay? So that's the reason why what typically is going to start to happen with these classes when we write those very first level classes is that we're now going to write them with an equals, hash code, compare to, all of that stuff included, just in case somebody wants to turn around and use them in one of these containers. Then all the work will be done and they can just use them. And so notice that in this case the friend class got fairly complicated in terms of having to write all this stuff, but the driver class is actually really, really small when you use the collection stuff to do the work for you. So we're starting to get to the end of the term where all of a sudden this is all coming together, and the idea is supposed to be now we've got these tools for your toolbox that you can use when you're trying to manipulate bunches of things in various ways. All of that work is going to be done for you as long as you're smart enough to put the right things into the classes that you're manipulating and dumping into the containers. And you got to know what those things are in order to make use of those facilities. And I'll show you the longer version of that tomorrow. We'll go through union and intersection. It's on the, it's in the source code if you want to go take a peek at it. And I actually added comments to that version of source code. But we'll just go through that one tomorrow really quickly to show you union and intersection because they don't have obvious names. See you tomorrow.